Right. So once again, nonlinear is anything which is not linear, so it is anything which is not satisfying the superposition principle. The superposition principle. Okay, let's go a little bit into details. Okay, so let's talk about some facts. Engineering sciences, they say here, they are mainly based on linear mathematics, algebraic differential linear equations, and integral transforms. Example. Let's have an example, okay? The linear mechanical oscillator. The linear mechanical oscillator. Or, as we know it, the mass spring damper system. No? Yeah? This is a mechanical system. This is characterized mainly by a second order differential equation, like most of the mechanical devices or mechanical phenomena, especially those based on laws, on motion laws, on laws of motion or motion principles. Okay, so essentially you have that acceleration, yeah, the force given by the acceleration, okay, plus some coefficient times the first derivative of the position. Yeah, y is going to probably be the position. Okay, so we have a spring, we have a mass, okay, and we do have here a damper, okay, and this may be a driving force or not, okay, and this may be the elastic force, okay, and then you may have also the friction force, okay. So essentially this is the motion part, mass times acceleration. This comes from mass times acceleration. Okay, this is usually the friction force, okay, which is directly proportional to the speed, to the velocity, plus another coefficient. I'm just making it very general because this is generating a whole class of systems. So with this type of equation, you can model an infinite number of phenomena. It's not just the mechanical system, okay? Plus B times, so this is the what? This is usually the elastic force, okay? Equals F, which is the input. Equals F, the driving force, which is the input, okay? Now, as we know, these are all linear phenomena. Why? Because we have linear friction, which is directly proportional to the velocity, and we have linear elastic force, which is directly proportional to the position. Okay? And this is the second order linear differential equation governing the class generated by the mechanical oscillator. Now this is a linear equation. This is linear. Okay? This is linear. It's easy to see that if here f is split into f1 plus f2, these are all time measures, yeah? So the position, this is yt, position, okay? Y dot t, this is velocity, and y double dot t, this is acceleration. We know that from mechanical systems. We know that from mechanics, okay? And from the physics itself. This is a second order equation because this is a second order based principle in physics. Okay. All right. So this is linear. So to solve this, so to find the solution y or y dot, okay, to find this, since this is linear, you can easily apply the Laplace transform. Of course, in the frequency domain, the Fourier transform. Integral, yeah, integral transformations. Okay, and then you can easily solve this equation in this fashion. Okay, The Laplace transform is very well structured. You've got tables telling you of the Laplace transforms of specific time domain functions called Laplace original functions, and so on and so forth. I'm not going to get into the detail of this because we are not very interested in this part. We have to leave this part. But essentially, when you apply Laplace, then you get the so-called transfer function of this mechanical system, which is from the position y, from the input f to the position y. This is transfer function, okay? Transfer function. Transfer function, and this usually means this is equivalent to saying that the output or the position ys is the transfer function times the input, and then you can easily apply inverse Laplace transform, and you get that the position yt is the so-called ht, which is called the impulse response of the system, in convolution to the f of t force. Okay, this is what happens, and then you can easily compute y using the Laplace inverse transform, because you have tables. Okay, but this is the main relation. Well, convolution is linear. Transfer function, this is a linear operation. What happens in the nonlinear case? What happens in the nonlinear case? So if you have the oscillator, okay, let's say that the friction is still linear, but you have a nonlinear function instead of the b coefficient here. This is a nonlinear function. And this is essentially, and we will see this example, this essentially describes a stiff versus soft spring. Okay, so with a nonlinear function, you can characterize stiff versus soft spring depending on this coefficient, on this real coefficient r. So you have soft, or depending actually on this whole function. Okay, this whole function defines soft or stiff spring, which you cannot do in the linear case. But in this case, there is no superposition whatsoever. You can no longer apply the Laplace transform, because this is the y square is not an original Laplace function. You cannot do this anymore. Okay, so the main question is, how do we compute y? Can we compute, main question, can we compute y? The answer is no, 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 not analytically. Not analytically. Here you could compute it analytically. Okay, so this is an analytic relation. This one here. This is an analytic. Sorry. This is an analytic relation. Okay. This one, not analytically. Not analytically. Okay, then how? We need to know something. Then we can say qualitative properties of the trajectories of yt. This is what we can do in the nonlinear setting. We can do qualitative stuff. Okay, not quantitative, I'm afraid, because it's very difficult to analytically compute. Well, in this case, So, like I said, facts. Engineering sciences are mainly based on linear mathematics. Yeah, based on superposition principle, convolution operation between signals. Okay, given by linear differential equations, and due to superposition principle, you can apply integral transforms like Laplace and Fourier to be able to quantitatively, analytically give a formula of the response of such a system to a specific input signal fed to the system. Okay, right. So everyone is saying, well, linear models work very nicely, don't they? Right. However, can they capture everything in the world and everything that happens within a specific phenomenon? Of course, the answer is no. So linear models do have limitations. Okay. So real science in the past, so in the years 80s and 90s, the nonlinear world was not existing because they canceled it. They said, we don't need all this fancy mathematics and the physics. We do not need that. That's not necessary, okay? Because we have our linear stuff, we can build PID controls and further later on Kalman control and all Kalman filtering and all this stuff, and that's more than enough. Oh, okay, then they built up robust stuff to treat nonlinearities as some uncertainties running against or running on the modeling and so on. However, it's still not enough. It's still not enough because there are some some phenomena which are purely nonlinear and cannot and their linearization, which we are going to study quite a lot, is not capturing very well the behavior. Yeah. For instance, they say nonlinear dynamical systems have penetrated in various fields of science, such as biology, weather forecast, chaos, fractals, and so on and so forth. Of course, the problem was that, okay, even if we can build a very nice theory, okay, even if we can build a very nice theory of nonlinear systems, it's very difficult to to compute something on a computer. It's difficult to create algorithms on the computer until they were smart enough to cook up numerical integration, which is the basis for why nonlinear dynamical systems have come back very nicely. Because MATLAB, and not only MATLAB, also, and we are going to study as well, and I'm going to let you discover Maple, a symbolic calculation tool, which is quite powerful, at least from a teaching point of view. From a research point of view, Maple has got a lot of limitations, and this is also mainly due to the computation power that we have. Since we do not possess any supercomputer whatsoever, or people are barely or starting to cook up or to buy supercomputers, Maple has got its limitations because Maple needs a lot of memory to be able to process and to give you back formulae, plural. Okay. Right. So the main motivation to discuss nonlinear is that also the computation power has come to the help of this. Not much, but very important. Okay. With numerical integration and recursiveness. So the conclusion is that linear models can be done away with, and we can come up with a new approach. Of course, this is not new. No, we are placing ourselves in time many years ago. Okay, so they were able to start thinking of nonlinear stuff once again. Okay, the question is, okay, fine, from a theoretical and computational point of view, I can understand my philosophy, but is this really needed? from a practical point of view? That's the main question. Okay, philosophically, mathematically, scientifically, this is very important. But does it have any bearing in real life? This is the main question. And the question and the answer is that the nonlinear phenomena themselves do provide us the answer, because there exist nonlinear phenomena which do not occur in linear time, which cannot occur in linear time. Okay, these phenomena can only occur, what they say here, can only occur in the presence of at least a nonlinearity. Okay, and the first thing that springs to mind, the first phenomenon, is the so-called finite escape time. Okay, that means that the solution to a nonlinear differential equation may possess a vertical asymptote. Okay. I'm talking to the Romanian students. In Romanian language, we do not directly translate finite escape time. Okay, because we cannot translate, and we actually call it in Romanian vertical asymptote. But this is actually what happens. So you can get from a nonlinear system a solution which is discontinuous, which is not possible with linear systems. Linear systems yield only continuous solutions. Why? Because essentially, if you have a linear system of this form, sorry, x dot, yeah, because this equation you can easily write it, this equation here, yeah, of the mechanical oscillator, this equation can be easily written. I'm going to write up here. This can be easily written as x dot is ax, where x is y and y dot. Okay, all right. So essentially, you can transform, and you can call this equal to x1 and x2. Okay, and from a second order equation, you can transform this into a first order equation, which is going to be governed by x1 dot is x2, yeah, because you have y dot equals y dot. Okay, because y is x1 and y dot is x2, you can easily write the first equation. And the second equation is x2 dot. x2 dot is y double dot. Yeah, this is equal to minus by minus minus bx1, sorry, minus bx1 minus ax2 plus f. Okay, and this is easily written as x dot equals ax, where a is the matrix 0, 1 minus b minus a times x. We know how to do that from linear system theory. Okay, we know this way of modeling. Well, so in this case, we have x dot equals ax. The question is, what is, so this happens for all linear equations, no matter the dimension of the equation. So if you have a 10th order linear differential equation, you can easily transform it into a 10th order dynamical system of first order differential equations in this form. And we know how to do that since second year, okay? Or from any basic control engineering course. We know how to do that, right? Fine. So now I have the system x dot, sorry. I'm telling you, I've got the differential system. X dot is ax with the initial condition x0, because we know that for dynamical systems, the initial condition is really important, okay? So what happens to the system initially? What is the response, the free response of the system, or the free evolution of the system when you have a specific given initial condition. So typically, what is the response of such a system? So if you have this system, what is x of t? Do you know how to solve this equation? This is a simple linear first order equation. How do you solve it? How do we solve this equation?
We separate dx and dt.
Exactly. So you separate the variables. So
And
let's
then
go back.
integrate.
Well, let's go back exactly. Let's go back to the scalar equation. X dot is ax with x naught is x of 0. You do separation of variables. So you do 1 over x dx, okay, is right, or 1 over ax dx is 1, okay, and then you perform integration. Here on the left part you integrate from 0 to x, and on the right part you integrate from 0 to t, right? Okay, yeah. So you have something like 1 over a ln x from 0 to x, from x0 to x, actually, not 0, x0 to x, from x0 to any x in time, and this is x naught, and this is x, is t, right? So essentially you have ln x minus ln x0 is at. True? You agree? So then you get that natural logarithm x over x naught. We know this relation of the logarithm. This is at. So you can apply the exponential function over all this, and you get x over x0 is e to the power at, which means that x of t, the solution of this equation, the free solution of this equation is is x0. It's x0 exponential of at, continuous function for all a real numbers. Now we can extrapolate this to matrices. We know that we have the exponential matrix, which is defined as the identity plus at through the Taylor series expansion plus a squared t squared plus, and so on and so forth. Okay, so there exists the matrix exponential. So sorry, you said something? No. So given the matrix exponential, we get that x of t is e exponential of at times the initial condition x naught. Okay, with x in Rn, x0 in Rn, and e to the power the exponential of at, a matrix of a square matrix of dimension n. But this is always continuous for all matrices A in Rn to n. This is always continuous. So this is never going to give you a vertical asymptote. Okay, this looks like this. Okay, or looks like this. But it never has a vertical asymptote. Okay, because we know that limit when t goes to infinity from e to the power at equals 0 for a. How is a if we want this to be 0? How is a supposed to be if we want this to be 0?
Negative.
Negative 1 for a equal to 0, right? And infinity for a positive. So it's always continuous. This is the main catch here. This is the main idea. This is always continuous. Well, in the nonlinear setting, however, we may get discontinuous solutions. We may get discontinuous solutions, and we'll see examples of that. Okay? This cannot happen, and I just showed you. This will never happen to a linear system. Is this clear to you? Is this clear to you?
It is clear.
Okay. So we have finite escape time. This is a nonlinear phenomenon. A second nonlinear phenomenon. Very interesting. Multiple isolated equilibria or equilibrium points. Multiple equilibrium points. Well, the linear system x dot is ax. What first of all is what is an equilibrium? If we have the nonlinear system x dot is fx, what is an equilibrium point? X star is an equilibrium point of this equation if and only if
that derivative is 0.
X dot star, very well, equals 0, or if and only if f x star equals 0. This is the definition of an equilibrium point. Well, if this is so clear, in the linear case, generically, I mean usually when the determinant of A is non-zero, there exists only one equilibrium point, and that equilibrium point is the origin. That's unique for linear systems. Okay? However, nonlinear systems may have more than one isolated equilibrium points or steady state, because that's what an equilibrium is, a steady state operating point. Okay? Steady state. We know what steady state is. Okay? Do we know? Are you familiar with the steady state term? Are you familiar with the steady state term?
Yes.
Okay. So this is an equilibrium. The example here is x dot is sine x. Okay. So the equilibrium points here solve sine x equal to 0. That means x is what? We have the sine function, yeah? This is the trigonometric circle. So 0, pi. Here the sine is computed on this part, okay? This is the sine. So when is the sine 0? At x equal k pi, k integer. Do you agree? Is it true? Oh, right. Thanks for the emoticon, right? For the emoji. So it's true. So you see, they're all isolated because k is integer. If k were real, they were no longer isolated. Okay, but this is specific very specific to nonlinear systems, okay, that they have multiple isolated points. For instance, one of the main examples we're going to discuss all throughout this lecture is the gravitational pendulum. Yeah, the gravitational pendulum. So, what are the equilibrium points of the pendulum? This is an equilibrium point, but also this is an equilibrium point, you see? But they're all isolated because in between them, there is no other equilibrium point. So essentially, this equation here is simplifying, yeah, is totally simplified pendulum. Is a totally simplified pendulum. Do you agree? I think you agree, right? Okay. Another very important nonlinear phenomenon, okay, very important nonlinear phenomenon, is limit cycles. This is also nonlinear. It can never be linear. That means stable and sustained oscillations in electronics are produced by nonlinear systems which can go in, this is limit cycles, can go into oscillation of fixed amplitude and frequency and never leave these oscillations. Linear systems, in linear systems, these oscillations, they are very, very non-robust because they can easily become unstable or the oscillations can die out. However, in the nonlinear case, the oscillations can be kept of a fixed amplitude, okay, of a fixed amplitude, okay. So essentially, what we're trying to say here, if you have something like y double dot plus okay, plus y, this is equals 0, okay. So this is a linear oscillator. That means that y of t is something such as sine or cosine t, okay. You can easily do the computation using Laplace transform, okay. So essentially you have this as, but here you can also get a linear term. You can easily get a linear term plus a y dot, and because of this a y dot, positive or negative, the oscillations can no longer be kept constant. They can either grow and become unstable, or they can also, if a is stable, they can also die out. So linear oscillations, they are not stable whatsoever. Not stable, sorry. They are not structurally stable in the sense that they cannot be kept at constant amplitude and frequency. Whereas limit cycles, this nonlinear, very famous and strange phenomenon, shows us that nonlinear systems can keep on an infinite time constant oscillation of fixed amplitude and frequency. That's why they are mainly used in electronics, such as the van der Pol oscillator. Maybe you heard of this Dutch term, van der Pol oscillator. And of course, chaos. Chaos is also a nonlinear, peculiar nonlinear phenomenon, okay? In the sense that a nonlinear system can have a more complicated behavior, which is usually not an equilibrium point, okay? And you can have periodic oscillation or almost periodic oscillations, okay? And despite the deterministic nature of the system, because the system is usually defined by equations, the behavior, if you plot the behavior, it looks like chaos, okay? And this is, deterministic nonlinear system may exhibit chaotic behavior, which is also something very peculiar to nonlinear systems. And you have to try this command in MATLAB, yeah, called Lorentz in MATLAB, and see the behavior of this. Let me see if I can start my MATLAB and try to show you what happens. Try to show you what happens. Okay. How do you find the things so far? They're very difficult. That's why I'm going to take it very easy and very short. This introduction lecture, I'm going to make it short. Okay. I'm going to make it very short because I think it's not very easy to grasp. How do you find things so far? I'm asking you because I need your feedback on this stuff.
It's pretty good until now.
Yeah, but it's not easy. Okay, this is not easy.
Mm-hmm.
Because this is telling you that there is a different philosophy of things, which is more general than what you have learned so far, right? Because essentially, most or the majority of the control theory and modeling you have studied so far is under linear perspective, okay? This is nonlinear, so this is different, completely different. However, you'll understand some very interesting things and concepts. Okay. So what I do want to do now, just want to show you some plots. Okay, some graphs, some simulations. Right. Okay. What I wanted to ask you, is it easy for you to join this class at this time of the day at 2 o'clock? Is it easy for you?
I'm working, but I can do it.
You can listen. You can attend, right?
No, I can pay attention. I can skip work for a couple of hours.
That's what I'm saying. So okay, so you can attend.
Yeah.
Okay, and how about the rest of you?
I work too, but I will continue my work after the classes.
Okay. So you can listen. Also, you can work if you're multitasking. You can listen to me and do some of your work as well. I mean, you can listen to me like a radio or something. You know. I'm not okay. So because I wanted to ask you if you like to keep these hours. Florian, what's your opinion of this?
I'm fine with that time too.
Oh yeah, because you're not working actually. You're just a student, right? Okay, so for you it doesn't matter.
Projects, but I can do it like really flexible, so it's fine.
Okay, that's fine. Okay, right. Okay, that's good because you know I hate to go very late in the evening because since we are online, why go late in the evening and ask you to pay attention at 7 o'clock? You know, when you're tired and you don't want you'd like to do anything else but study. I think this makes sense, right? So we're going to keep it this way and try to, of course, I don't expect you to be at 2 o'clock sharp because you see, I couldn't make it at 2 o'clock sharp. We have enough time in 4 hours because I think 4 hours is a bit too much every week, but we have enough time in 4 hours to discuss and do our stuff and stop and do breaks and do everything. Okay, so I think we can be flexible. Do you agree? Do you agree we can be flexible?
Yes.
Okay, fine. Right, so okay, let's first I'm preparing the MATLAB and then I'll share a different screen with MATLAB, okay? So we can look at some simulations, right? Okay, open. So let me try to share a different screen. All right, can you see my MATLAB screen?
Yes.
All right, and let's just type in Lorentz. Sorry. You see? I'll show you one of these lectures. I'm going to show you the 3 equation based model. So this is a model of 3 differential equations, deterministic. Look at the behavior. Can you see? Can you see the behavior? Yes or no?
No, I just
We-
can see.
Okay, let me share different. Let me share the full screen. Okay. Can you see the full screen? Can you see the blue graph?
Right now it's visible.
So look, this is the chaotic behavior of a deterministic nonlinear system given by 3 equations. This is called a Lorentz attractor. Okay, it's called a Lorentz attractor. I'm going to show you the model. I'm going to show you the model. This is a 3rd order model. Okay, this is a 3rd order model. Right. So let's try to go back to our class. This is to the other screen. Okay. Can you see the other screen now? Huh? No. Let's try again. Share screen. Can you see? Yes, you can. Okay, because I am on 2 devices, so I can see that. Right. No, where were we? We were here. Okay. So we have the Lorentz attractor. Let's see if I can find. I'm sure I can find in my materials the equations for this guy. Okay, so right, classes. Let me try to show you the model. Yeah, look. So the model is made of three equations. Okay, x1 dot is a coefficient s times minus x1 plus x2. So this is a very normal equation. x2 dot is rx1 minus x2 minus x1 x3. So nonlinear term. And x3 dot is minus b x3 plus x1 x2. And this is the second. So look, it's very harmless. This guy is really, really harmless. But these very simple and very weak, and we'll see what weak means. Very weak nonlinearities do exhibit the chaotic behavior of this very quiet and very very non-nasty, let's put it this way, system. Okay, very interesting, right? You agree? This is not very easy. Okay, right. So we are dealing with what happens with mathematical modeling of phenomena and industrial processes. Okay, this is mathematical modeling is of utmost importance, and before you can do any kind of control whatsoever, okay, the first thing you have to do is you have to get yourself a very good model. You have to get yourself a very good model. What is mathematical modeling? Essentially, mathematical modeling is, it used to be until today, writing equations describing how different variables are related to each other. Nowadays, people do not write so easily equations any longer because the complexity and the dimension of the phenomena which being under study, okay, is increasing, is constantly increasing. Hence, it's quite difficult to be able to write hand by hand a number of analytic equations. So what people do nowadays, they do modeling from data, or how it is actually called, data-driven modeling. Okay, but in this lecture we are going to focus on nonlinear classic modeling. However, and even easier, we're going to work under the assumption that throughout this lecture, the models are provided. We do not have to get the models ourselves. The models are provided from somewhere else, okay, or by someone else, okay. So we have input-output data-based models, that system identification and data-driven, and currently the modern or the nowadays data-driven modeling. And we also have models based on equations issued by physical laws, such as which is the Newtonian approach, like we saw in the mechanical oscillator approach. Yeah? We saw that in the mechanical oscillator approach. Right. Okay. So we have input-output database models and models based on equations from physical laws. Right. When elaborating a model, they say here, one has to do a trade-off between the complexity of the model and its accuracy. That only makes sense. Okay. You cannot have a simple model and extremely accurate, and you cannot have an inaccurate model if it's very, very complex. Usually, when you want to capture more, you have to cope with increasing the dimension and or the complexity of the system. Okay? Do you agree? Right. Okay. What is a good model? When the differences between the experimental results and the calculation results are smaller than the specified tolerance. This is when we can call a model a good model. Okay. Nonlinear dynamical systems, they are usually appropriate models, more accurate and better understanding of phenomena. They are very complex. They are more complex than the linear systems, but like I said, increased complexity means increased accuracy. They are sort of like directly proportional one to another. Okay. Methods and concepts are tailored, of course, to engineering practice, even for nonlinear systems. And for instance, one very nice domain you can get through this difficult modeling, you can get revolutionary applications such as mathematical modeling of genetic circuitry, for instance, or for instance, more classical a little bit is the modeling of power systems. Okay, all that's related to power generation and power storage and so on. This is nonlinear systems. They are very appropriate for that. Okay, a little bit of history, and I think maybe we should call it a day after this historic slide. So Isaac Newton, everything starts from Isaac Newton and his laws, differential and integral calculus. So based on this approach of integration and of integrating and differentiating, evolutions or trajectories are obtained integrating the equation x dot is fx, just like we did with the linear equation x dot is ax. Yeah, and we did this example a short while ago. Okay, using simple differential equation theory, okay, such as separation of variables, when it's possible. Of course, when the equation is more complicated, or the dimension of the nonlinear differential equation is increased, then it's extremely difficult to be able to perform things like separation of principles. You have to use other methods. Okay? Then, for nonlinear system, there comes in, of course, once you did the differential geometry, you have, and you talk about trajectories, then you have to go to geometry. And we have the geometry of the trajectories in the state space. The thing is that this is not simple Euclidean geometry as one would expect. This is actually differential geometry, which is very, very difficult, and we unfortunately, or fortunately, actually, we do not study in this faculty. Differential geometry is cumbersome and tedious and extremely difficult. Essentially, in differential geometry, to write the equation of this trajectory from point A to point B, essentially you need like 10-15 pages. Well, I'm exaggerating. At least you need a few pages of equations and formula and things, very difficult concepts to be able to write or to express this curve. Differential geometry is very difficult, but is very suitable to nonlinear control. Please do recall that linear control is also a geometry of the state of the space Rn. Okay, image, kernel of those operators. Okay, all sorts of matrices with different sparsities. Those are geometrical aspects, algebraic geometrical aspects. Whereas here we need differential geometry to be able to understand and to do some control. We are not going to get very much into the details of this because it's extremely difficult, and since you do not have the mathematical background for this stuff, we're going to slightly touch this point of differential geometry in the very last chapter of this lecture. You know, when we talk about feedback linearization, because for feedback linearization, which is a control, nonlinear control procedure, we do need some differential geometry aspects and approaches. And of course, it's very interesting, then the concept of stability popped up from the Russian Lyapunov. Okay. And the idea was how the solution of the trajectory changes at small variation of the initial conditions or the parameters of the system. Okay. And it's based on the idea of continuous dependence between initial conditions and parameters. Okay. This is a very interesting concept because essentially this is related to the concept of energy. And the stability, the way Lyapunov has defined it, is based on the internal energy of the system. Essentially, a system is stable, and actually you will see that stability is no longer a property of the system, but a property of an equilibrium point. So an equilibrium point is stable, like we saw with the pendulum. Yeah, this point is stable because the energy of the system around this point, so if the pendulum is slightly swinging back and forth, small variation here and there, the energy developed is fading away due to friction, due to other things. So the energy is fading away. So this is a stable equilibrium point. That's what Lyapunov is telling us. Whereas this equilibrium point, the minute you take the slightest variation of this equilibrium point, the pendulum and the energy of the pendulum is increasing, and the pendulum is never coming back. Well, the energy will go to zero, but will go to zero again at this equilibrium point. Here, Here, at small variation, the system never returns to this point. So this is an unstable. This is an unstable equilibrium point. So the stability now is in this Lyapunov concept. This is stability of equilibrium points, not of system. Of course, when we are able to talk about global properties of stability, then we can also call the system stable, but this is quite rare. Usually, this is local stability of an equilibrium point and of the motion or the behavior of the system around this equilibrium point. I know this is very fuzzy right now, but we are going to clarify these concepts once we formalize everything mathematically. We are going to talk about a lot of mathematics here. I'm sorry, but this is nonlinear systems. I can't do it otherwise. And of course, more recent history, well, numerical integration has changed everything and has brought back to the front ground these nonlinear systems. Okay, we have numerical integration of differential equations. Okay, by discovering the sensitivity to initial conditions, chaos factor, one can analyze the evolutions of complex systems. Okay, right. Of course, we are going to talk about some mathematical preliminaries and start defining basic concepts. We have to build what I like to call a legal background. Okay, we need to be we need to be legitimate about things. So we need a mathematical background to be able to be legitimate about things, such as, is there a solution of such a system? When does there a solution? When is a solution existing? And so on and so forth. The concept of solution, which was very easy in the approach of linear systems, is more difficult here because essentially you have to consider nonlinear systems of specific classes to be able to define classes of solutions of nonlinear differential systems. Of course, we're going to work with a specific class which is very suitable for teaching and for building and for helping these concepts penetrate your mind. Is everything all right? Was I kind of clear today for you?
Yes, of course.
Yes.
Maybe I have a question. Can you
Please?
maybe describe one non-linear system we could like see in our daily lives, maybe as an example that I have like a
Yes.
understanding?
Well, I gave you the pendulum stuff. The pendulum. You said you worked in automotive industry, right, Florian?
Like
Or automation? Yeah. Automation or automotive?
Automation, more or less.
Okay. Well, in automotive industry, for cars, anything that is talking about braking system or suspension system, these are nonlinear things. This is nonlinear stuff. Actually, everything around us is nonlinear, but we just linearize it. I was talking earlier about the mechanical oscillator. Or let's take maybe electrical engineering is more familiar to you. Usually take an RLC circuit, okay? Usually the L, the C, or the R also may contain nonlinear parts, like nonlinear resistors. All the phenomena around us are kind of nonlinear, right? Because, for instance, springs, they are stiff or soft, I just showed you earlier. Whereas in our approximation, we consider them linear, okay? With an elastic constant. This is usually this is not the case, okay? Now, what else can I show you? Because we have also a power system. Contains swing equations and contains nonlinear stuff, nonlinear coupling of mechanical and electrical variables. Okay, this Lorentz attractor I just showed you a minute ago. Okay, and many other things. But like I said, the pendulum is the basic example for this stuff. For instance, we have in the lab where we cannot access now due to COVID and the restrictions, we have a flying system. Okay, all this system from aviation, from aviation industry, they're essentially nonlinear because they contain sines and cosines of angles. But usually in control, people linearize these things. Okay. I'm not sure if this is exactly what you have been expecting, but we'll see along. Oh, for instance, what we have, I'm going to show you next time an example of hunter predator game system. Okay, this is nonlinear.
Okay. Yeah.
What
Okay.
is-
I
Sorry.
think I have heard about things like that before because I was like wondering. I was at first like thinking of like a resistor or something, which is like I would say from like the model how the output-input relation is, it's linear, but I think that's just an approximation. So
Yeah, it's an approximation. That's right. For instance, all in electronics, you have diodes, right? These are
yeah.
not linear because they contain hysteresis. They contain everything that contains saturation, hysteresis. These are specifically nonlinear phenomena.
Okay.
They are strong nonlinearities, actually. Any saturation, any hysteresis. And then for those strong nonlinearities, you need different concepts of solutions of the systems.
Okay.
Like the tunnel diode, this is, we will have an electrical example later on. The tunnel diode, this is, or the Josephson junction, these are nonlinear things. Okay, like I said, an electronical oscillator, because you need oscillations in electronics, you generate them with limit cycles, with nonlinear oscillators, because they are structurally stable. No matter how you perturb such a nonlinear oscillator, it will always oscillate constantly or come back to its constant oscillation. You see?
Okay. Okay.
If you have any other questions, please. If you got more questions, please.
Currently not. Maybe just one more thing. Do you have some kind of like some literature in the English language you would recommend?
Certainly. It's in English and French language, actually.
Okay.
It's all I can cover. Yeah, the main book to understand these things, I'm going to put it on Moodle, is the
Okay.
book of Hassan Khalil, which is the Bible of nonlinear systems.
Okay.
It's English. It's a huge book treating nonlinear systems. Very good. Actually, this lecture is based on that book.
Okay.
And it's
Yeah,
an English book, of course.
I just sometimes like I think like the basics are really important to understand the rest of it, and most times I'm like hanging because my basic understanding is not that good at all. So
No problem. So I'm going to upload a series of literature resources. Okay, but listen, do take advantage of the internet. You can also find different nonlinear lectures. I also have a book of nonlinear systems and chaos, if you're interested. A course taught in Hamburg. I can show you that as well.
okay.
Okay.
Yeah, I'm just like I need to admit, like I pushed like all the control stuff to the end of my master's. So right now I have everything here. So I try to get ahead of it because I need to.
Listen, if you have any questions about linear and nonlinear control, or you need some material, I can share with you quite a lot of material in English, and I have many electronic English books, more or less legal, but that's not for your concern. Um, and I can share them with you if you're interested. So
Yeah, that would be nice. I will start like looking up some things as soon as I get to the point
I
where.
can share with you because I keep most of this stuff on Google Drive. You know Google Drive. I'm sure you're familiar
Yeah.
with Google Drive. So I can share you through Google Drive folders where you can find a lot of material.
Okay, that's
Let's
nice.
see. Or I can precisely give you stuff. I'm also going to upload quite a lot of stuff for this lecture.
Okay.
Because this is a research master, so you have to do individual study quite a lot. You listen to me for a couple of hours and then you can go and look up anything you need. Okay?
Okay.
All right. Anything else, please?
I have one a little bit maybe more general question. Like
Please.
I also enrolled or tried to enroll for a module called like a research project or something like that, which should be like give 10 points. How does that work? How do I get like a topic I have to work on, or?
That's for people. No, that topic is for people who do their master thesis here.
Okay.
I'm not sure you do your master thesis here.
No, I won't do that here.
You're just visiting.
Yeah.
So you'll have to ask at the secretaries, or you'll have to ask. Who do you have to ask? Ask also my colleagues, because there are more lectures at this class in this master
Okay.
program.
Yeah.
Ask them, because I cannot tell you precisely how you have to deal with that research course. So
Okay.
that is, as far as I know, and your colleagues Andre and Theodor can confirm, that course on Moodle is for master thesis students, I think. So I'm not sure how, and of course for them it's a course, so they are going to be graded at that research. But I'm not sure how this works for you for your Erasmus program. So you'll have to ask your Erasmus.
Yeah, I will do that. I was just like wondering, maybe you can give me like some.
Who is your Erasmus leader, or
I think it's Mr. Sakala or something like this.
Mr. Sakala? So
Or-
ask Mr. Sakala.
Yeah.
He's a vice dean. So
Yeah.
you should ask him, look, what am I going to do with this class called
Yeah.
research project? Because that's dedicated, as far as I'm concerned, that's dedicated to people doing master theses.
Yeah, it was not my idea. It was like brought to me by some of my colleagues with which I had a discussion in May about which.
Okay, maybe there is a way for you to make a small project and submit it and present it, and maybe you get extra points which can be very useful, or credit points which can be useful to you. So if you can make the best of this discipline, of this lecture, please try to do so, but ask around. I'm not in the best position to tell you precisely what's going on with this class of research project. However, if you need help with it, or I can accommodate you as to the best of my knowledge. But for the time being, I think you should ask around how you will have to deal with this.
No worries, I will do that. But thank you for your help so far.
No problem. Anything else?
From my side, I think that's everything. And thank you very much again.
No problem. Let me, so you guys can, I'm going to prepare a WhatsApp group as well. Do you agree?
Yeah, from my side, it's okay.
I'm going to share the link of this WhatsApp group on the general channel of this class, of this Teams class. You'll see it written, and you can join using that link. You can join the group. Okay? You can also contact me through these Teams personally and also in the class. Okay? You'll have to check Moodle for I'm sure Florian, you're registered on Moodle, right?
Yeah, I'm registered.
Okay, if you're registered there, you can find materials, and there is going to be the report book, for the grade book for you, for all of you. Okay, So we have to use Moodle, okay, for everything concerning material stuff and okay, uploading and downloading stuff. And we can also use the file section of this Teams class. That's easy for me. I can upload here, for instance, I can upload MATLAB files, which you can download, and Maple files, which you can download. And okay, I'm not sure, Florian, do you have MATLAB or Maple installed, or both of them?
Currently, I think I have MATLAB on that machine, but I also can download it from my university. That should be no problem.
Okay, see if you can download Maple as well from your university. Okay,
I'm not familiar yet with that one. I heard it, but I think I will manage it to install it.
Try to install it, because you can run some Maple sheets which are already written by myself, and you can look at formula, and you can look at simulations and graphs, and this is very interesting. I think you should learn how to use that, because it's a good skill for you, and for all of you, actually, the rest of you as well. You have Maple, or I'm going. Okay, for the rest of our university is not supporting Maple licenses, so I'm going to give them another version they can install Maple on their machines. Okay, Andrei, Theodor. Okay, I'm asking them. Yeah. So for you guys, I'm going to give you a Maple kit, to install. Okay, because
from my perspective, I don't know also if I have access to like a Maple license.
You can ask at your university. Anyway, I'll put the kit on Moodle or on the Teams class, and you can download it as well.
Okay.
You'll read the instructions on how to install it.
Yep.
The others not to know, so to speak. You know what I mean? Okay. Yeah. Right. Anything else, please? Okay, I'm going to stop the recording at this point and ask you again if you have